right, so we're looking at page 11, section 1.1, 4 ways to represent a function. One of the reasons that I love our textbook, I've talked to you before about how readable it is and how easy it is to understand. But the other thing that I love about it is from day one specifically preparing you for the AP exam. On page 11, they talk to us about we're going to stress that a function can be represented in 4 different ways. By using an equation, by representing it with a table of values, utilizing a graph, or expressing it in words. Why is that so important? Well, let me take you over to College Board's website. So this is from AP Central, from College Board. This is actually out of the AP Calculus AB course description. So if you'll notice, one of the very first things that they say in their philosophy is that the course emphasizes a multi-representational approach to calculus, with concepts, results, and problems being represented or expressed graphically, numerically, analytically, and verbally. If we go down the very first goal of the things they want you to accomplish, students should be able to work with functions represented in a variety of ways, and here are those same 4: graphically, numerically, analytically, and verbally. So our textbook just said that they're going to present all of our functions in 4 different ways. They said that they were going to represent it algebraically, where we would represent it with a formula. So you can see that here as well when they're talking about analytically. They're going to represent them numerically with a table of values. There it is right there, numerical. They're going to represent them verbally in words. There it is right there. And they're going to represent it visually with a graph, and AP is just saying graphically, right? So from our very first lesson, that's going to be our emphasis all the way through. So there on page 11, they go through and they give you A, B, C, and D, 4 different scenarios. Of the first one there in A, they represent a function with an equation. So that's the algebraic, analytic, formula, whatever of those names you want to give it. For B, the numeric or tabular version there, where they give you like the population over the course of a year. So that would be like the numeric representation. For C, they give you a word problem, so that would be obviously verbal. And then for D, they give you a graph, so that would be the visual or the graphic representation. The other thing that we want to be sure that we can do is work interchangeably between those 4 methods. So, for instance, we would like for them to be able to give me, let's say that they give me a table of values. I'd like to be able to take that table and graph it, and then from that graph, either myself or have my calculator do a regression to generate an equation or a formula that would fit it. And then from that, I could justify my reasons for why I did what I did, or give the theorem or the postulate or the definition that was associated with that in terms of justifying my answer. So that's how I could interweave those 4 ideas together. So over on page 12, they remind me of what a function is if I want to represent it 4 different ways. So a function is a rule that assigns to each element x in a set A exactly one element called f of x in a set B. Every x must have a y value, and no 2 x values can be the same. Remember, we do that vertical line test to check for that? So every x has to have a y, and no 2 x values can be the same. Now, you can have 2 y values that are the same. There's no problem with that. And you can have y values that aren't assigned to an x. So there's not a converse to that. Every x must be assigned to a y, and no 2 x values the same is our informal definition of a function. So there on page 12, they go through and they start off giving us quite a few bold print terms. They talk to us about function, as we just mentioned, and then they move into domain and range. Now, What's domain? All right, the values that we associate with x. What's range? Values we associate with y. So what happens if I have a scenario that doesn't have x and y? Like the situation they just gave me was population over the certain number of period of years. There's no x and y in there. There's probably a p for population and a t for time. Then what do I do? Okay, my horizontal axis is going to be my domain, and my vertical axis then would be my range. So in just a second, we're going to talk about then how do I figure out what goes on the horizontal and the vertical axis. So hang on to that a second. And then they talk to us about variables versus constants. What's a variable? Something that changes, something that varies. What's a constant? Something that stays the same. It stays the constant. Stays constant. So, although the numbers and the things that we're going to work with this year are going to vary from one extremity to another, what are some of the constants in life? Death and taxes, right? What are some of the constants in life? Do we have any constants in life, or is everything a variable? Nothing? I would like to think that you have some friends that are constants for you. I mean, they may not be perfect, but I'd like to think that you can always depend on them. They're always there for you. They're a constant. I would like to think that your mommy and daddy are constants for you, or at least somebody in your family is a rock for you, or somebody that you can always depend on. I would like to say that I'm a perfect friend and a perfect parent, but I'm not. I mean, I'm going to be variable sometimes when even I don't want to be. I'm going to make poor decisions or poor choices that affect other people. And I hate that, but that's just part of being human and our human nature. So the only thing that I can think of that is a constant in our life that does not vary, that we can always depend on, that is always there for us, is God. I love the verse in James 1:17 that says there is no variation at all with him. Not even the slightest shadow of him turning or changing or turning away from us. So that we know he is the one constant. When anything else would fail, he's the one constant that's always there for us. No matter where we go, if I'm on the opposite side of the world and my parents aren't with me, he's still there for me, and I can always depend on him. So I love that God's a constant. He's not a variable. All right, we mentioned when we were talking about domain and range that we tend to think domain X, range Y, but in most of the scenarios we'll be looking at this year where we're looking at problems, it's not going to be X and Y. So when we're looking for what to associate with our domain, yes, we are going to graph the domain value on the horizontal axis, and we're going to graph the range value on the vertical axis. But when we're looking for what goes there, the independent variable is going to go on the horizontal axis. The dependent variable is going to go on the vertical axis. So that's why, typically if you're graphing something like y equals 3x plus 2, you put values in for x and they determine what y is, right? Y depends on x. That's why y is called the dependent variable and x is called the independent variable. So go back to that example we had a few minutes ago about population. Let's say that we were looking for the population in Savannah over the course of 10 years, okay? What's the dependent variable? What's the independent variable? Does the population depend on what year it is, or does what year it is depend on the population? Yeah, the population depends on the year. I don't get to go set the calendar, right? I don't get to go back in time and change time, and yeah. So the population is going to depend on what year it is. So in that case, population is my dependent variable. I'm going to graph it on the vertical axis, and the time or the year that it is going to be my independent variable. I'm going to graph it on the horizontal axis. So my domain would be associated with the time, and my range would be associated with the population. So we'll have to look at the particular scenario that we're working with and determine which is dependent, which is independent. That'll help me with domain and range. Another way of thinking of domain and range is input versus output. Your domain, your input values, the values that you are plugging in that then determine what the other value is, what your answer, what your outcome is going to be. So that's another easy way sometimes if you're having a little bit of trouble with the scenario that you're in. Look at what you're putting in and what you're getting out. Domain associated with input and range associated with output. And so there on page 12 they talk about, you could think of it as like a machine with input and output, or you could do like, they give you an arrow diagram there with some mapping that might help it click for you as well. Okay, so when we talk about independent and dependent variables in relation to, we were just talking about variables and constants. There are lots of things that we have to depend on other people for. You depend on your parents, most of you, for food and clothing and shelter and, the money for all the things that you need and your education and that type of thing. And so you're dependent on them. You get to the point, however, that you'll be independent of those things. We tend to, I'm an extremely independent person, but there are some things that I cannot provide for myself. I'm always going to be dependent on God for my salvation. There's no way that I can provide that for myself. So no matter how independent and self-sufficient I become, I still have to depend on Christ. And that goes back to that awesome thing that I can depend on Him. He is that constant that has no shadow of turning. So that's the perfect place for me to put my trust and to put my dependence. Ephesians 2:8-9 says that it's just by grace that you're saved. It's there's nothing that I can do on my own. It is a just flat out gift from God that I accept. There's no way I can earn it for myself. I am completely dependent on Him for the most important thing in all of this life. So, all right, let's look over on page 13, example number 1. Page 13, example number 1. It says the graph of a function is shown in figure 6. So find the values of f of 1 and f of 5. That's that function notation that we've become accustomed to. F of 1. What does f of 1 ask me to do? All right, put 1 into the function in the place of x and find the y value. Yes. Okay, so I'm going to put 1 in the place of x in my equation. Oh, I don't have an equation. Okay, here's that multiple representation of functions again, right? If this notation means put 1 in the place of x and find y, then I'm going to come over here to my graph and I'm going to say when x is equal to 1, what's y? Well, look at the ordered pair. When x is equal to 1, I have that ordered pair 1, 3. So when x is equal to 1, then y is equal to 3. So f of 1 would be 3. All right? How about f of 5? What would f of 5 be? 0, right, because we can look at that pair 5, 0 and see when x is equal to 5, y is equal to 0. All right, what is the domain of this function? All right, well, I don't know. I don't have an x or a y. I don't have an equation. We don't need it, right? Because remember that we said the domain is going to be associated with the independent horizontal axis, and the range is going to be associated with the dependent vertical axis. So I can look at this. I'm going to give my domain an interval notation. So I want the lowest value on the left and the highest on the right. So I'm just going to start over here with the lowest values and say, okay, what's the first value that I hit on my x's? 0, right. And I'm going to keep going. What's the last value that I hit? 7. So my domain then is going to be from 0 to 7. Brackets or parentheses? Brackets, because I was equal to 0 and 7. Same idea with the range. We need our lowest value, so let's start at the bottom and work our way up. So what's the first value that you get to? -2, and what's the last value that you get to? +4. So my range is going to go from -2 to +4. And again, I'm using brackets. And if you look at that going, well, I don't know, am I equal to those values or not? Well, think about it. When you have this point up here, if your graph is going through that point, then you've got to be equal to that value, right? So the only reason you wouldn't put a bracket there, the only reason you put a parenthesis is if there was literally an open dot on the graph right there showing that you did not go through that point. Okay? All right, so look at example 2. For example 2, it says, sketch the graph and find the domain and range of each of these functions. So for the first one, they give me f of x is equal to 2x minus 1. Remember, f of x and y are the same thing. So you can graph that line however you want to. Since it's in slope-intercept form, I would probably say since my y-intercept is -1 and my slope is 2, I'll rise 2, run 1, rise 2, run 1, get a couple of points, and I've got my line. Or you could make an xy chart, take some y-intercepts, whatever you want to do. So looking at my line, what is my domain? What values did I use for x? All real numbers, yes. So depending on how they want it, if they want interval notation, I'm going to say negative infinity to positive infinity. If not, I can just use the symbol for all real numbers. Remember, that's that capital R with like the double bar. How about range? All real numbers, same thing. Negative infinity to positive infinity, we used all of them. All right, look at the next one. For the next one, we've got g of x is equal to x squared. So again, you could write that as y equals x squared. We just covered that in our appendices with those second-degree equations, so we know what that graph is going to look like. But if it was something that you didn't know, you could just plot points and generate your graph. So looking at my graph, what is my domain? All real numbers, right? What is my range? 0 to infinity. Bracket or parenthesis with 0? Bracket. Bracket or parenthesis with infinity? Always, without exception. Infinity and negative infinity, always going to have a parenthesis. All right, so then over on page 14, they go through and do a little more discussion of the introduction that they had given us about how to represent functions in the 4 different ways. And they go back to the A, B, C, and D examples that they gave you at the beginning and just expound on them a little bit. Let's look at a couple of additional examples to see what we're using this multiple representation of functions for. Example 3. It says, when you turn on a hot water faucet, the temperature, capital T, of the water depends on how long the water has been running. Draw a rough graph of the temperature as a function of the time that has elapsed since the faucet was turned on. Now, they were kind to us because they basically went through and helped us figure out the independent-dependent variable thing, right? So when you turn your water faucet, you turn your hot water on, and you maybe just turn the hot water on, the temperature of your water is going to depend on how long that water runs, right? So we can understand what they're saying there, that the temperature depends on the time. So you'll notice that they have put the temperature, capital T, on the vertical dependent axis, and they've put the time on the independent horizontal axis, okay? And they want me to just kind of sketch the graph. So when you turn your hot water on, is it 100 degrees? No, what is it? It's probably like whatever, probably close to the temperature of your house, right? Or depending on where your pipes are, because it's whatever water's been laying in your pipes, right? So am I going to start down here at 0? Not unless your pipes have exploded, right? Because water freezes at 32 degrees. I don't want to be down here at 0 saying that's where my hot water temperature is starting. They did not give me a scale, so, I can just kind of choose where I want to start. So when I turn that water on, what happens as we progress along this timeline? It slowly goes up, right? So it gradually increases. So I'm going to start not at 0, just somewhere up that line, and I'm going to gradually increase. All right, then what happens? To what? I do start losing hot water, but something happens before that. It plateaus. Why does it plateau? You have a hot water heater in your house that is set to some temperature. So it heats the water to that particular temperature. So when you turn the hot water on, you've got that water that's in the pipes that has to run through, and then the hot water starts coming in, so you have that gradual increase. But whenever it gets to whatever temperature the water is set at on your hot water heater, it's going to plateau and it's going to stay there. Until what? all that happy water is gone, and then what happens? Then it goes down. Does it go down nice and easy and gradually? No. It's like all the hot water is gone, and then all of a sudden the temperature of the water like plummets and you're freezing, right? Then what happens? And then it plateaus again, right? Because once all the hot water is out of there, then it's going to level off and continue running at whatever the regular temperature is. And again, that's going to depend on, where your pipes are in your house, and it's going to depend on what season of the year it is, and it's going to depend on where you live, and, so that's why they've left this very ambiguous over here, because it is not a set quantity. It could be a varying thing based on those conditions. But we were still able to take a verbal representation of information and represent it graphically. All right, look at example 4. Example 4, they also want me to give a graphic representation, but this time instead of giving me a verbal model, they give me a numeric model in a table of values. Example 4, the data shown in the margin comes from an experiment on the lactonization of hydrovaleric acid at 25 degrees Celsius. I don't have a clue what the lactonization of hydrovaleric acid is. AP loves to give me random examples I have never seen of, maybe even never heard of before in my life, and ask me to apply calculus to it. Because that's a true measure of I'm not just regurgitating something that I've learned and memorized how to do. I have that higher thinking skill of being able to apply what I've learned to whatever scenario that they would give me. So this is very typical of them presenting me with something that I'm very unfamiliar with, just to see if I can do the math associated with it. It says they give the concentration, capital C of T, of this acid in moles per liter after T minutes. Okay, so does the concentration depend on the time, or does the time depend on the concentration? The concentration depends on the time. So as time elapses, that concentration breaks down and breaks down and breaks down. So absolutely, you can see that we're putting the concentration on the dependent vertical axis. We're putting the time on the horizontal independent axis. So if we go through and it says use the information to draw an approximation of a graph. So I could go through, they gave me 0.08. So there's 0.08. They gave me 2.057, so I'll come over here to 2 and just a little past the halfway mark there, between 0.04 and 0.05 maybe. 4.04, so we'll come over here to 4 and go up to 0.04. 6.0295, so I'd come over here to 6 and maybe go about halfway in between 0.02 and 0.04. And then 8.02. 8.02. Then it says use this graph to estimate the concentration after 5 minutes. They didn't take a sample at 5 minutes. They took a sample at 4 minutes and at 6 minutes, but not at 5. And if you look at this, this is not linear. So I can't just do like a handy-dandy midpoint formula or an average or something like that to find the value. So instead, what I could do is I could look at this and say, if I generate the graph from that information that they gave me, then I could come over here to where I think 5 is and kind of trace that up and have a good approximation of what that value might be. Now, this is an extreme approximation. I'm going off of just a couple of values that I've hand graphed on a hand-drawn, I could make this more accurate if I, maybe used graph paper and used a bigger scale and was a little more precise, or if I used my graphing calculator to do the graphing, because it's extremely precise, right? So let me just remind you of the process that we learned last year. We will be doing this over and over and over again this year, so this is just a brief review, but we'll go back through this extensively later on, okay? So just a review of how we did regression last year. We went to statistics, and we went to edit, and we put our information in list 1 and list 2. To plot statistics, we go to second y equals, which is stat plot, and I turned it on and chose a scatter plot for the information in list 1 and 2, and I chose the little blocks to use. And then I went to zoom and let my calculator set the window for me by going down to number 9, zoom stat, and there's the graph that looks just like the one we had on our paper, only it's much more precise. I could look at that and I could kind of zoom and trace and try and figure out maybe approximately what that value was. Or I could get my calculator to do a regression and create an equation that fits that information, and then I'd be able to plug 5 into that, right? So that's exactly what I want to do. Looking at this, it kind of looks like it has a curve shape to it. So I might first think parabola. You know, parabola kind of has that curve to it. But if it's parabola, then the concentration is going to have to turn and start increasing after a certain amount of time. Is that going to happen? No, concentration of the quantity is not going to go back up. So it's not linear. It has that curvature to it. And if you think about it, as time goes on and on and on, that value is going to get closer and closer and closer to 0, like an asymptote. So what has that kind of shape in an asymptote at 0? Exponential function, maybe? So again, we'll be reviewing those types of functions in this chapter as well. So here's our exponential function. I'm going to choose exponential regression then. So I go to statistics and I use my right arrow key to go over to calculate and go down to exponential regression. If I also enter y1 after that, it'll automatically load the equation in y1 for me, so I don't have to. So it gave me the regression and it auto-loaded it in y1, and so then there is the graph of that equation. Okay, so here's the deal. We took something that was represented numerically in a table of values, we switched it to visually with a graphic representation, and now we've switched it to an algebraic representation where we've created an equation to fit it, right? And then we can utilize that equation to go through and plug in 5. So I just used the value feature on my calculator to plug in 5 and to get that much more precise estimate. Still an estimate, but much more precise. All right, so we've spent a lot of time today talking about domain, and it's the value associated with our independent variable. Your domain is going to be all real numbers unless a couple of things happen. Your goal is to put a value in for the independent variable that will then generate a value for the dependent variable, right? Put something in so that you actually get a real output. What is not a real output? What would be the only things that we would have to watch out for? Imaginaries. What else? Undefined, yeah. So undefined comes from 0 in the denominator. Imaginary comes from a negative under a square root. So that's why we have to watch out for those limitations. I cannot have a 0 in the denominator. I cannot have a negative under an even indexed radical like a square root or a fourth root. Additionally, sometimes the problem that I'm working with will have its own constraints. Like, if I'm working with a distance, like a radius or something like that, it can't be negative, right? So sometimes the situation I'm in will cause an additional constraint. All right, so example 6, we've got f of x is equal to the square root of x plus 2. So we do have a radical. We don't want a negative under that radical because it has an even index. So what am I going to do to find my domain? Take what's under the radical and do what with it? All right, set it equal to 0. Set it greater than equal to 0. Yes, so nothing wrong with setting it equal to 0, but it also can be greater than 0, right? It just can't be less than 0. So anything else is fine. So for my domain, I can take what's underneath the radical and set it greater than or equal to 0, and then I can just finish solving that. And typically they want our answer in interval notation. All right, how about g of x? We have 1 over x squared minus x, so we definitely want to avoid that 0 in the denominator. So what do I need to do? All right, it can be positive, it can be negative, it just can't be 0. So take our denominator and say it is not equal to 0, right? So if I go through and I solve that, I'm going to get x equals 0 and x equals 1. Those are the two things that my domain cannot be equal to. So I could say all real numbers except for 0 and 1. If I want that in interval notation, I start at negative infinity, and when I get to 0, I got to pick up and jump over it and start a new interval. So then I can go from 0 to 1, and I got to pick up and jump over that and start a new interval, and then I can go from 1 to infinity. So there's my interval notation. All right, we mentioned at the beginning of the period that a function can have no two x values that are the same. So we had a handy-dandy easy way to check the graph of a function to see whether it's a function or not. What is that? Vertical line test. Why does the vertical line test work? What does it do for me? Vertical line test says if I draw a vertical line and I hit my graph in no more than one spot, so I don't have to hit it all or I hit it once, but no more than once, I can't hit it twice or more than that, then it is a function. Why? Okay. No two x values the same. What is that vertical line looking for? Two x values that are the same, right? If I go through and I have a graph and I can draw the vertical line so it hits the graph in no more than one spot, that means that every one of those x values were different. But if I draw a vertical line and I hit that graph in two spots, if you think about that, if these were ordered pairs, that might be like -1, +2, and -1, -2. That's two x values that are the same. That's why we get to use the vertical line test, because that is exactly what it is looking for. No two x values the same. Okay? All right, so here is our homework on pages 22 and 23.